ionospheric reflection or anything like that. So typically you're looking at, maybe a couple of watts being, a useful amount of power. This transmitter here, this power amplifier, is considerably bigger than that. This is rated at 70 watts. Now, when I say it's rated at 70 watts is the point at which the gain starts leveling off. So it'll actually deliver a lot more than 70 watts. It'll actually deliver about 100 watts, which in RF terms is a huge amount of energy to be dumping into UHF. It's actually not tremendously difficult to get hold of even bigger amplifiers. This does 600 watts. This was recovered from an old analog mobile phone station, which also just happens to operate in the same band. So this is 600 watts of RF, and quite honestly, at UHF, that's a terrifying amount of power. It's really quite scary. I mean, you'll get RF burns off of this really easily when it's powered up. I actually didn't bring the power supply for that, just specifically because it's too scary given the kind of crowd that comes to these events. So we'll stick with the 70 watt amplifier for this demo. We're not even cranking it up anywhere near the maximum. This was $400 online. And the thing about RF amplifiers is they don't tend to have volume knobs. You can't just tweak the volume up and down. What you have to do is limit the input power to it in order to control the output power. They have fixed gain. So we've got a maximum, an upper limit on this power amplifier of 20 milliwatts power input. We've only got 10 milliwatts coming out of the IME, so we need to amplify that up slightly. I don't know if you can see, there's a tiny little amplifier in this cable, little miniature thing with these power clips connected to it. That amplifies it up to plenty of power to drive the power amplifier, and then the USRP, we attenuate the signal down to match that, and we're all good. It's not tremendously difficult. It's all off-the-shelf parts, mini circuits and Down East microwave, pretty common supplies for this kind of stuff. So we can increase our range, we can increase our power. What can we use to try and quantify this? Well, we noticed a pretty interesting artifact on the read range in that there's going to be one of two situations happening here. When we try and read a tag at long distance, there's going to be one of two things happening. Either it'll read or it won't. And if it doesn't read, then it's going to be because either this transmitter isn't supplying enough power for the tag to switch on, or alternatively, the signal that's coming back from the tag isn't enough to register on the receive side. So we need some way to differentiate the two so that we know if we need to up the transmit power or up the receive gain. And the way that we can do that is by looking for hysteresis on read range, because the tags require an initial burst of higher power to turn on. Once they've gotten that higher startup current, they'll actually drop down in power consumption. So if you look at that in terms of the power available to the tag being directly related to the read range, you'll have to bring your tag closer to the antenna, at which point it'll switch on, and then you can take the tag further away from the antenna before it switches off. So if we see that hysteresis on read range, we know that we're limited by transmit power. Alternatively, if we're limited by receive gain, then we'll just see a single point where if we go too far, it turns off, and if we're too close, it turns on. So depending on whether or not we see that hysteresis on read range, we know whether we need to increase the transmit power or the receive gain in order to bump up read range. And in both cases, those follow the radar range equation. So what are the limits on range here? We've got 1.5 kilowatts that we can put out of the antenna, and we're restricted to whatever antennas we can get hold of. So really the power output and the antennas aren't really our limits anymore. The primary limit that we're going to come across is noise and interference. There's a lot of different sources of noise in the ISM band. Obviously, other ISM stations, other transmitters on the same frequency. Receiver sensitivity, there's going to come to a point where the signal is just plain too weak to be picked up. And the most sensitive amplifier that money can buy still won't be sensitive enough to pick up that signal. That's going to be a limit eventually. There's also going to be crosstalk between the transmit and the receive side. We have got two separate antennas, because we actually do full duplex communication on a single channel. So obviously, we're transmitting a carrier out to the tag, and the tag is modulating that carrier back to us. So there's no way that we can stop energy from the transmitter coming directly back into the reader. We can't do it because it's on the same frequency. Clutter is another source of interference, and this is a big one. This is where there'll be reflections from other non-metallic, from other metallic items that are, reflecting power. We've got a radar system here. So anything that's metal is going to be reflecting our radio energy back at us exactly the same way that any radar system does. So any metal objects in the vicinity, I suspect the backs of the chairs are going to be a problem, probably the back wall of the room. There's going to be all kinds of spurious signals coming back at us here. And eventually, those signals are going to swamp the real signal from the tag, and we just won't be able to read it. Ground interference. Well, we've got our Yagis pointed, pretty much horizontally out across the audience here, but they've got a 15-degree beam width. So there's a few degrees up and a few degrees down that energy is still directed. So some of that will be reflected off the ground before it hits the tag, which will scramble the signal at the tag. Likewise, the reflection that comes back from the tag, some of that will be reflected off the ground again, and again it'll confuse our reader. So we can improve things by, lifting it up off the ground. The antennas aren't just so, the antenna stands here aren't just so that we can, see over your heads. It's also to reduce this ground interference. Atmospheric effects. Well, the radar range equation is great, but it's only valid in a vacuum with no other transmitters and no noise and a perfect receiver and a perfect transmitter and all kinds of other things. In the real world, the air gets in the way of these transmissions to some degree and attenuates it somewhat beyond what the radar range equation predicts. And then eventually, when we get to really extreme ranges, we're working with UHF, which does not reflect off the ionosphere, so we're restricted to line of sight, and eventually just the curvature of the Earth is going to get in our way. Hopefully, if we can get that kind of range out of it. So if we put all of these parts together, we've got 1 watt of RF power coming out of the commercial reader, and we've increased that to 70 watts with our power amplifier. That's an 18 dB gain in power. So from the radar range equation, we would expect to see the square root of that in range gain, so we'd expect to see 9 decibels increase in range. From the antennas, well, the commercial reader started out with 6 dBi and we went to 13 dBi. So we've got 7 decibels gain increase in the antenna system, which means we should see a 3.5 decibel increase in range. So comparing that all together with our 30-foot reference range, we should see an overall range gain of 12.5 decibels over our 30-foot read range. So we would expect to see 565 feet if we're running this transmitter at full power. What did we actually get? 217 feet. Not the 500 we were hoping for, but 217 feet. That's a long way to read an RFID tag from. You can see in this picture here, there's all of my equipment in the foreground. You can see these Yagis bolted to the top of the car just on the far side. And then you can see my wife in the background holding an RFID tag up. That was reading successfully at that distance. That picture wasn't actually the final read range. That picture was at about 180 feet. We didn't get a picture of the final range because we were kicked out by Google campus security. Apparently they don't like big, powerful radio transmitters in their abandoned lots. Can't imagine why. So why so little? Why do we only get 217 feet rather than the 565 that we were expecting? Well, first off, 217 feet, as far as I'm aware, that's still a world record. The only 2 other instances that I've been able to find of people reading passively powered RFID at long range, Flexilis did a demo in 2008 at Blackhat where they demonstrated 70 feet of read range, or 69. And then there was a talk that a chap called Ravi Papu from ThingMagic gave at Google, where he claimed 213 feet, I believe it was. So just scraped by with a record on there. But the thing of it is, that was with 3 watts of RF power, at least 3 watts as indicated by my little meter here. In reality, it was a little more than that because the transmission is pulsed and this meter reads average power. So it was actually, if you calculate it out and kind of work out how much power is coming out and how much I'm attenuating it and all the various losses in the chain and the gain of all the different amplifiers. I calculated out at about 10 watts. So the thing of it is, we did obviously have the capability to significantly increase power beyond 10 watts, but we actually found that increasing power decreased the read range. And the likely reason that we found for that, if you look in the top left corner of this picture, this is actually an abandoned lot beside the Google campus, and the tent that you can see in the background is Shoreline Amphitheater. You can see there's a big chain link fence that runs around Shoreline Amphitheater. That was a source of clutter. And as it turned out, there was so much energy being reflected from that chain link fence that it was swamping the signal from the tag, and putting in more power increased the amount of clutter, decreased the read range because it decreased the signal to noise ratio from the tag. So nonetheless, we're still consistent with the radar range equation. 10 watts, 217 feet, 13 dBi of antenna gain, that still matches the radar range equation. But there's no way that this equipment is limited to 217 feet. It's absolutely possible of significantly more than that. And if someone is able to find me a suitable test range, I'm willing to demonstrate it. Obviously, I've got all the equipment here. I believe that this equipment will read at 1,000 feet. And I think probably the best way to demonstrate that is if it's possible to get access to a roof in Vegas. Because then you can shoot the antenna down at 45 degrees and any reflections go out away from you and don't cause clutter. So I'm perfectly willing to set this all up and try it for a 1,000-foot read. Certainly 217 feet is what I've demonstrated so far. So quick demo of long-range tag reading then. Let's see if this works. So for some reason, my machine here that I'm using, it doesn't want to talk to the projector, so I'll have to show you on the screen here. It's pretty easy to understand though. So I don't know how many people, can you at least see something on the screen here? The idea is, if you see white text, that's a signal from the tag. It's some kind of something. It's interacting with the tag in some manner. If you see red text scrolling past, it successfully managed to read a tag, but the ID number that it got back failed the checksum. So it's a successful read, but failed the checksum. And then you'll see, I think it's blue that scrolls past to show a successful tag read. So what I want to do is, I'll start the software up here. I'll turn the power amp on. Okay, so you can see white text scrolling past. That means it's doing something. So what I want everyone to do is notice that the antennas, the elements go vertically. Now, what that means is that the energy that comes out of this is vertically polarized. So the orientation of the antenna has to match the orientation of the tag. So if you look at your tags, you'll see the thin metal stripe goes sideways across the tag. You want to hold it so that that stripe is vertical. Okay? And in theory, if you hold up tags, you should see, so bad reads coming through, there's all kinds of stuff scrolling past. And if the first 5 rows can put their tags down, and we'll